This is going to be the 8th lecture on the series on metric spaces. And we are going to do what you had been waiting for, continuity on metric spaces. As is our typical thing, we will start with the definition, which is an easier definition than what is usually available in books and practiced by teachers. But finally, we will end up showing our definitions equivalent to some of the standard definitions. And as is our practice, the concept of continuity will be illustrated with our chosen list of metric spaces. Okay, so that you will have a very good idea how to work with continuity in a metric space context. Okay, so let us get started. Okay, so what we want to do is I have a metric space XD and another metric space YD. Okay, these are metric spaces, right? And you remember I don't write dx dy. You will understand the reason for that. So what do I want? And suppose a is a subset of x, right? And suppose f is a function from a to y, a function. Okay, I don't think I have to recall the definition of a function to you. Anyway, this is a function, right? And fix a point. Okay, call it x in a, right? I want to define f is continuous at a, at x in a, right? So what is my definition? This is all I have to look at. Okay, f is continuous at a if for every sequence, okay, xn in where in a, okay, I have sequence f of xn. Okay, where is this sequence? This is a sequence in y, right? Now you notice that why the sequence must be in a, because f of xn must make sense. Okay, right. So what do I want for every sequence xn in a, so that I'm not taking all sequences, but with the property xn converges to x. Okay, you understand this? So I will draw a picture also in a minute. For every sequence xn in a, so that fx xn converges to x, we have the sequence of xn converge to fx. Okay. See, this definition is a little easier, but at the same time subtle. Why it's subtle? So let us look at first picture. This is my x, and this is my y, and this may be my a. Okay, what I am taking? I have point x. I have a sequence of points xn which converge to this. Where are xn's? Xn's are here, and their images are f of xn. And this is your f of x. I will denote by a different color. This is f of x. These are all fxn's. Okay, so what do I want? If xn converges to, let me denote this also xn. So if xn converges to x, okay, then I want, then fxn is a sequence in y, it should converge to fx. All right, is the definition clear? And for which sequence you should hold? You should hold for every sequence. So I may have another sequence. Let us say, let me use a different color. Okay, this may be another sequence. Let us call it yn. Not no, let us call it tn. Tn converges to x. Therefore, I have the corresponding sequence. Okay, this is f of tn. What do I want? F of tn also should converge to fx. That is, for every sequence xn and a, if you tell me xn converges to a, then I have sequence fxn and I have a point fx. These are all in y. Then I want fxn should converge to fy. Okay, please pause, review, proceed. Okay. Now, even before looking at example to appreciate definition, okay, let us look at what are the things. Suppose I say f is as above, f is not continuous. at x. What is the meaning? See, f is continuous at x and a, it says for a sequence xn and a, so that xn converges to a. That is, you look at the set of all sequence xn and a, so that xn converges to x. Take any such sequence, something must be true. So if f is not continuous at a, what does it mean? It means there is a sequence xn in a, so that xn converges to x, but the sequence fxn does not converge to f of x. Do you follow that? So there exists a sequence xn in a, so that xn converges to x, but fxn does not converge to fx. Does not. Okay. This is not maps to symbol. You understand that? Okay. The next thing you can ask is, what is the meaning of fxn does not converge to fx? There are two things. First, the sequence fxn may not even converge. That's one possibility. Okay. And second possibility is fxn may converge, but to a different limit, but to a limit y which is different from fx. You follow that? If f is not continuous at a, let's go back to the definition. There is a sequence for which the conclusion fails. So what kind of sequence I should look at? There is a sequence xn in a which says that xn converges to x. Okay. What conclusion? fxn must converge to fx. That fails. That means fxn does not converge to fx. Now we want to understand what is the meaning of fxn. The sequence fxn does not converge to fx. What are the possibilities? There is no reason for me to expect why fxn must converge. Okay, so it may not converge. Next, the sequence fxn may converge, but it may not converge to a limit. It may converge to a limit which is different from fx. Okay, please pause, review. We will look at examples to explain all these things. Okay, right. So let's look at some. With these definitions, we'll start, and these two things can happen. We will illustrate. Okay, in the simplest case of our favorite example. So let us look at example. First spaces x equal to r. Okay. So let us look at, okay, let A be a subset of R and from to R and fix a point X. Okay. What does it mean to say fxn converges? This is a standard notation. If xn converges to x, xn's are in A, then fxn converges to fx. This is the definition. All of you know that. Yeah. These are all ordinary real sequences. Okay. So let us look at a very concrete function. Suppose f from R to R are even a subset. F R, let us say f of x equal to x squared. Okay, you will see the beauty of our definition. Okay, now suppose fix a point x in A and start with any sequence xn which converges to x. What I have to prove? I have to prove fxn converges to fx. But what is f of xn? Xn squared. What is f of x? X squared. What do I have to prove? Xn squared converges to x squared. Is it true? Now do you see the beauty? You had already learned in real analysis, if xn converges to x, yn converges to y, xn times yn converges to x times y. Therefore, xn squared, that is xn times xn, converges to x times x. So these are true statements. So what does it show? This is continuous. At what point? At x. What is x? Any x in A. Therefore, f is continuous on A. If f is continuous at each every point of x, we say f is continuous on A. Therefore, what we have proved is f is continuous on A. Right? The same proof you can do for any n natural number also. Any natural number. Right? Okay. Now let me look at A equal to, let us say, R minus singleton 0. And what is my function? X going to 1 by x. So f is from A to R. It's actually R star, but anyway, let me. Is it continuous? Okay. Let us fix x in A. I want to check continuity of f of t. What is it? I have to check. Let xn converge to x. Now notice that where are xn's? Xn's are here in A. Therefore, none of them is 0. Therefore, fxn makes sense. I have to check whether it converges to fx. But what is fxn? It's 1 upon xn. What is fx? 1 upon x. I want to know whether it converges. Again, this is following from algebra of convergence sequences in real analysis. Right? If xn converges to x, if xn's are non-zero, x is non-zero, then you know 1 by xn converges to 1 by x. Okay, this is a fact from analysis. So you see that this is the beauty of our definition. Okay, now let's look at the same thing, a case. All right, let us look at f from R to R, so that fx equal to minus 1 if x is 0, 0 if x equal to 0, and equal to 1 if x is positive. Right? I want to know whether it's continuous. Yeah, at 0. What point? I want to know whether f is continuous at 0. This is a question. Right? Now you know that I have 0. I can take 1 upon n. Right? Obvious thing is I can also take minus 1 upon n. These are the two sequences. Or I can do minus 1 to the power n minus 1 by n. That is, the sequence consists of 1, minus 1 by 2, 1 by 3, minus 1 by 4, and so on. Yeah? Now where does this sequence converge? Of course, this converges to 0. But what is f of xn? F of xn is at 1, it is 1. Okay? Therefore, the sequence f xn, I will simply write it as a sequence 1, okay, minus 1, 1, minus 1, etc. Do you follow that? This is not convergent. Do you follow that? So in particular, it does not converge to f of 0. F of 0 is 0. It is not even convergent. Therefore, the question of f of xn converging to f of 0 does not even arise. You see that? This is what I said. This happens. Okay. Pause, review, proceed. The same example slightly we will modify. F is again from R to R, and f of x equal to 1 minus 1 if x is less than 0, and equal to 1 if x is greater than or equal to 0. Right? Okay. Now what happens? Let us look at. Now suppose look at the sequence xn equal to 1 by n. Then xn converges to 0. What is f of xn? That is 1. Does it converge to f of 0, which is 1? Yes. So can I conclude f is continuous? Can we conclude? No. Why? We are supposed to prove this for each and every sequence xn converge to 0. So we chose one sequence for which it happened to be true. You follow that? But let us look at this sequence yn, which is minus 1 by n. Then yn also goes to 0. What is f of yn? F of yn is minus 1. Therefore, where does f of yn converge to? It converges to minus 1. Is it equal to f of 0, which is 1? No. Now you see that the second thing happens. F of xn may converge but to a limit, but it is different from fx. So what do you conclude? F is not continuous. So we conclude f is not continuous at 0. Please pay attention. So this example is very trivial, simple example, but illustrates a lot of things. Okay. When a function f fails to be continuous, and also not only it also says why. The definition says for every sequence xn something must happen. In the last case, what happened? For the sequence xn equal to 1 upon n, things are very good. But the moment I choose a different sequence, things go bad. So to check continuity, It is important that I have to check each and every sequence xn in A which converges to X. What should happen? Fxn should converge to Fx. How can it fail? Fxn may not converge, or Fxn converges, but to a different limit other than Fx. Yeah, I think this is a good place. Okay, that's a good time to make. So we will move to some other example now. Please pay attention and do that. There are a lot of examples. If I keep on doing it will be like real analysis. So I don't want to do that. Okay, I want to get along to the next example. Okay, let us just stop for a moment. It will come. So as we said, we are ready for the next example. Okay, let us start sharing. Can you guess what should be the next example? Yeah. Yes. This fellow has gone in sleep mode. Yeah. Come on, man. It should, yeah, right. Okay. Now, next example is something to do with RNs. Right? Okay. As usual, let us start with n equal to 2. So, R2. Can you think of some obvious functions from R2 to R? I have an ordered pair xy. Okay, I want a real number out of this. What do you think you'll do? I think there are two obvious choices. Can somebody guess? X plus y. And G is X times Y. Okay, aren't they obvious? Yes. Right. So what do you want to do? We want to know whether it's continuous. Okay. So fix X comma Y in R2. I want to know whether F is continuous at X comma Y. So I'll take Xn, Yn, which converges to XY in R2. Now notice that when I want to check continuity, I should have a metric on this. Right? I had been kind of just like that saying continuity I want to check, but it doesn't make sense unless I have a metric. What is the metric? It could be either D1 or D2 or D infinity. Okay, you will see it does. Okay, my D will be any one of these things. You fix once and for all, fix and work with it. It does not matter. You will see why. Now suppose X and Yn converge to XY in D. Right? We know that X and Yn converge to XY in D1 if only if it converges to in D2 and if only if it converges to D infinity. Therefore, it does not make any difference. Do you understand that? That's why I had been very generous. I don't care about what the metric D is. Do you follow that? But we have seen something very interesting about convergence of sequences in Rn. Do you remember what it is? The sequence of vectors converges to the vector if and only the corresponding coordinates converges. That is, this happens if and only if xn converges to x and yn converges to y. Yes, we had already seen this. This is already seen. Okay, right. Now let us look at it. Then what am I supposed to show? I am supposed to show fx and yn. I have to check whether it converges to f of xy. But what is this guy? This is xn plus yn. And what is this? This is x plus y. I want to know xn plus yn converges to x plus y. But now you see that again the advantage of our definition. X and yn converge to xy if only if xn converges to x, yn converges to y. This is a sequence of real numbers. And from algebra of convergence sequences, you know if xn converges to x and yn converges to y, xn plus yn converges to x plus y. Therefore, this is correct. That means f of x and yn converges to f of xy. That implies f is continuous at xy. I'm sure G also you can do the same way because G of x and yn will be xn times yn. Again, you know algebra convergence sequences, xn converges to x, yn converges to y, then xn, yn converges to xy. That's it. Yeah? Do you follow that? So how easily we got those things? Okay. That's the advantage of our definition. Similarly, G is continuous at xy. This also, okay. Again, go through if you are. Okay. But there is one very interesting thing which you would like to look at. Okay. What is that? Yeah. Now we looked at Rn to R, but I can ask, suppose X is a metric space and F is a function from X to, let us say, R2. Again, it could be Rn, but let us do that. Yeah, maybe I should give us an exercise here. Suppose, let us look at Rn cross Rn to Rn. Okay, given an ordered pair. Okay, is there an obvious map? I'm sure all of you have gone through linear algebra. Therefore, this is X plus Y. Okay, can you check continuity on all of this? And what is the metric on Rn cross Rn? Yeah. Now you can think of it extras y. If you want, we will come back to this example later. Okay. But anyway, keep thinking about this. Okay. You can do that now. Right. Okay. I have, okay, this is the next example. Suppose f is up, right? Then remember f of x. Maybe I should write it as instead of x, let me call it as something else. T. Okay. T is a metric space. Do you mind it? Okay. Okay, as I want to write xy for R2. Therefore, f of t, this is a vector in R2. Therefore, f of t will be some x and some y. Do you understand? This x will depend upon t. Therefore, you can denote by x of t, y of t. R usually only writes as f1 of t and f2 of t. Do you understand how this is done? If you want, let us give an example. Okay, let us look at what you want the set to be. Okay, let us take the set to be something. Yeah. Okay, so the set T is all human beings. Okay, and F is from T to R2. What is the function? Given a human being, this is his height of T and this weight of T. This height is in centimeters, this weight is in kilograms. Okay, or if you want grams, it doesn't matter. You understand that? Therefore, what is my F1 of T? Given a human being, what is F1 of T? F1 of T is his height, his or her height. And what is G1 of T? Sorry, F2 of T. So this I will call F1 of T. This is called F2 of T. These are called components. This is by definition his or her weight. Okay, I have to specify the units. Here the weight, height is in centimeters, the weight is in grams. Do you understand this? So these F1 and F2 are called components of the function F. Okay. So F of T I will write as F1 of T and F2 of T. So this is the x coordinate. This is the x coordinate of the vector f of t. This is the y coordinate of the vector f of t. Make sure that you understand. Okay. What do you think I would like to say? Suppose, let us look at, suppose Tn converges to T. Okay, T is a fixed point. Fix it. I want to check continuity. Let's assume it's given. Given f is continuous at T. Okay. Therefore, give me any sequence Tn converges to T. Then what do I know? F of Tn converges to f of T. Right? Not if and only if, simply this. Okay. But what is f of t? F of t is f1 of tn and f2 of tn. Right? Now what are they? They are vectors in Rn. And what do I know? This converges to f of t, but that is f1 of t and f2 of t. Do you understand this? Therefore, this sequence converges to this vector, sequence of vectors. Now again in R2, we know that this sequence converges to this vector if and only if this happens, if only if f1 of tn converges to f1 of t and f2 of tn converges to f2 of t. You follow that? Yes. So what do you think I have shown? I have shown that if f is continuous at t, then f1 and f2 are also continuous. That is, if only if f1 and f2 are continuous at t. You understand that? Now converse. Okay, pause, review, proceed. I have written if and only if very loosely, but if you want, let us just say only this way implication. So f is continuous at t. Let Tn converge to t. Therefore, f of Tn converges to f of t. Therefore, by working through, we found f1 of t1 converges to f1 of t, etc. That shows f1 is continuous at t, etc. Right? Okay. Now converse. Suppose f, I write it as f of t as f1 of t and fn of t, f2 of t. Therefore, f1 is a function from x to r and f2 is also a function f to r. Suppose I am given f1 and f2 are continuous, right? So I want to know whether f is continuous. Do you understand that? So I can cook up a function f from x to r to know. Okay, how do I cook up? Start with continuous function f1 and f2 from x to r. Define f of t equal to f1 of t, f2 of t. I am going to prove that f is continuous, but it's utterly trivial. I'll go fast. So fix a t in t. Let tn converge to t. If tn converges to t, what do I know? This implies f1 of tn converges to f1 of t because f1 is continuous at t. Similarly, f2 of tn converges to f2 of t. Right? This implies f1 of tn, f2 of tn converge to f1 of t, f2 of t. Why? That is how the convergence happens in R2. Right? But what is this? This is f of tn by definition. And what is this? This is f of t by definition. Right? So I have proved f is continuous. Okay. Pause, review, proceed. Right? Okay. Now let's look at the earlier example which I did and similar thing. Okay. Let's look at Rn cross Rn to Rn given by xy. This is the vector addition. Okay. Call this as alpha. Then I also have a scalar multiplication sigma, which is r cross Rn, okay, to Rn, where the scalar t and a vector s goes to the scalar multiple of x. Okay. I want to know whether they are continuous. Alpha, sigma, continuous. But then I should mention what is the topology, right? On Rn, remember Rn, I could start with any metric d, where d is d1, d2, d infinity. And on Rn cross Rn, I will use the product metric. Okay. Therefore, what is the distance between? Take xy, uv. This is by definition maximum of distance between x and u and distance between y and v. You understood? Right. Okay, I'm keeping the same metric on this Rn as well as that Rn, but even that is not necessary. But I don't want to confuse you. Just assume it's the same metric on first factor Rn, second factor Rn also. Okay, right. Now I want to know whether it is continuous. Alpha is continuous, let us say. Are you following me? Okay, just bear with me. These are the kind of examples people are very, kind of don't want to do it, thinking that students won't understand. But I believe all of you are good. Okay. If I just give you an idea, you will be able to understand much better. So that's what I'm doing. So let us go through that. Yeah. Since I had used Rn here, so let us say, so x is a point in Rn. Let us fix a sequence xk which converges to x and yk which converges to y. Right? Now I have sequence xk, yk, and let us converge to xy. This is where this is in Rn cross Rn. And remember, this is a product metric. In product metric, we know this happens if only if xk converges to x and yk converges to y. Do all of you agree with me? Yes? Right. So what am I supposed to show? Alpha of xk, yk I want to know whether it converges to alpha of xy. But what is alpha of xk yk? It is xk plus yk. I want to know whether it is same as x plus y. Right? But that's very easy. Why? Because what? Are you following me? Yes or no? Okay. This is very easy. Why it's very easy? Because remember, if I write this as xk1 xkn plus yk1 ykn, and similarly x1 plus y1 plus, this is not the same one, xk yk. That's why I should have chosen, like last time, bk and uk, and it converges to ub. Okay, do you mind it? Okay, anyway, right, this x1 x2 should not be confused with this. Okay, I'm sorry for the goofing. If you want, let us put a vector notation for the time being. Now usually this is what, xk1 plus yk1, and similarly xkn plus ykn. I want to know that it converges to x1 plus y1, etc. Right? But what do I know about that? I know xk converges to x. Xk converges to x if we know exponentially of xk I converges to xi for all I, where I'm writing xk is ith coordinate of xk, xi is ith coordinate of x. You know that, right? Are you following? Please bear with me. Okay, don't get confused. Okay, therefore, and similarly yki converges to yi. But remember, this is a sequence of real numbers, right? Xki is a sequence of real numbers which converges to the real number xi. Similarly, this. Therefore, their addition also converges to their addition. Therefore, this fellow converges to this fellow, and this fellow converges to this fellow. You follow that? And in Rn, how do convergence takes place? Coordinate wise. Okay. So I have proved alpha is continuous. Okay. Some of you will struggle here, but please pause, spend at least a minute or two, go through it. Okay. I don't want to explain too much. If I explain too much also, you think it's always too difficult. It's not difficult. But for the notation, it's very, very easy. The same way I proved R2 to R. Yes. Okay, the addition is continuous. It's exactly the same kind of proof. Okay, please go through it. Okay. Then the next example in Rn, this is the last example in Rn. We will move on to the more general case later. This is the case. Now suppose I have Rm, Rn, and I have one of the metrics. Fix any one of the metric. Here the metric will be D corresponding to R, D1, D2, D infinity. And similarly D, which will be D1, D2, D infinity corresponding to Rn. Okay. Notice that I'm going to use the same D. I'm not going to distinguish. Now suppose T is a linear map from Rm to Rn. It's a linear map. I want to know, is it continuous? At let us say B. B equal to B1 to Bm. Yeah. Right. This we will write as x1 to xm. Okay. How do I prove that? First, this is where, as I said, the knowledge about the subject is important. No. Okay. This is a fact I'm going to use, and you can look at my linear maps video. There I have proved this. Any linear map is of the form T of x1 to xm will be of the form. Okay. I will write a summation notation. Yes, x1j, xj, j equal to 1 to m, and 1 to m here, and j equal to 1 to m, a, n, j, xj. Okay. I hope all of you know this. This is m. Let me just make sure all of you follow this. Okay, this is a fact. where these are all scalars, right? Now, suppose you give me a sequence Vk which converges to V, therefore this will be xk1, xkn. This converges to, let us say, x1 to xn, sorry, m, because these are all in Rm, right? Then what do you have to check? T of this, whether it converges to T of this, right? But do you see that it is very obvious? Why? But what is T of this? In place of xj, I have to write this. So for T of this object is nothing other than the same thing. A1j x. Now I have to write kj. And j is running from 1 to m. And similarly, the last one. A n j x kj j equal to 1 to n. Right? Now, this happens, we know if and only if xkj converges to xj for 1 less than or equal to j less than or equal to m. Right? Therefore, xkj converges to xj and a multiplication by a1j into xkj converges to a1j times xj and summation of that thing converges to sum. Okay. This converges to this converges to this. But what is this? This is T of x, T of v. Yeah, this is T of vk. Right? So this is a convergence now. But this is equal to this. So what do you think I have proved? I have proved any linear map is continuous. Again, if you are very uncomfortable, please spend at least a couple of minutes to go through this. Okay. So what you have shown is any linear map from Rn to Rn is Rm to Rn is continuous. Material of any linear map. You see that in general a map may not be continuous from Rm to Rn. But if I know T is linear, it has to be continuous. Okay, that's something very interesting. Okay. And next is, before we close, we'll look at an example of discrete metric space. Xd is discrete. And Y is any metric space. Okay, not necessarily discrete metric. And suppose F is a function from X to Y. Okay. I want to know continuity. Okay. Let it sequence xn which converges to x. In this metric space, I want to know whether it converges to f of xn. To f of x. Right? But remember, we had already seen the convergence of sequences in a discrete metric space. How many of you remember? If xn converges to xn, then after certain stage, all my xn will be equal to x. Right? There is an answer that this happens. Eventually constant sequence. You understand? Therefore, in this, I will have fx1, fxn. After that will be, even here it will be fx, 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 fx. So this also eventually constant sequence. Therefore, it converges to fx. Are you following? So what do you think I have proved? You start with any function f from a discrete space to any metric space. I do not know what is y, what kind of a metric space y is. But the only thing I know is x is a discrete metric space, right? And what do I know about f? Nothing. F is just a function from x to y. And what do I know about x? Any arbitrary point of x. What do you think I have proved? F is continuous at x. Therefore, what do you think I have proved? Any function from a discrete metric space to any metric space is continuous. Something fantastic. You see that? Okay. This is a wonderful space. I don't have to check continuity. Okay. The moment you give me a function from a discrete metric space to another, it ought to be continuous. Life will be simpler, right? If that happens. Huh? You agree with me? Yes. Let us pause for a while and then start again.